Welcome to A Conversation with History. I'm Harry Kreisler of the Institute of International Studies. Our guest today is Steve Squyres, who is the Goldwin Smith Professor of Astronomy at Cornell University. He is the chief scientist and principal investigator of the Mars Exploration Rover Mission. That mission is described in his book, Roving Mars. Steve, welcome to Berkeley.
It's a pleasure to be back.
Where were you born and raised?
I was born and raised in southern New Jersey, right across the river from Philadelphia.
And looking back, how did your parents shape your thinking about the world?
Oh, they shaped my thinking in an enormous way. I have been a scientist as long as I can remember. When I was 6 years old, I considered myself a scientist. I just wasn't a very good one yet. Both my parents were scientists. My father is a chemical engineer, actually got his doctorate from MIT. My mother was a zoology major at Wellesley. That was where they met in Boston. And so when I was growing up, when I was a little kid, I was always interested in science. And I would go to my parents with questions, and Dad would handle all the physical sciences, and Mom would handle all the life sciences stuff. And so if I was looking through a microscope at cells, I would talk to my mom, and if I was, building a weather station out in the backyard, I would talk to my dad. And they were both very encouraging and remarkably tolerant. I was one of those kids, I had a little chemistry set, and I would do experiments that would, sometimes not do great things. Things would blow up and burn and so forth. And they put up with a lot.
So, but I get the sense that not only were you developing your science curiosity, but also somewhere you were getting the notion of being an explorer in a way.
Yeah, very much so. When I was young, I was fascinated by the history of exploration. I would read books about exploration of the Arctic and the Antarctic, mountaineering. I love climbing mountains myself. We took a family, I grew up in New Jersey where it's flat, but we took a family vacation to Colorado when I was 8 years old, and I just fell in love with mountaineering and climbing mountains. And what initially drew me to geology was I liked science, I liked climbing mountains. I figure I could do science in the mountains. Mm-hmm. And so that was what initially pulled me into geology. But yeah, and the other thing, of course, was I grew up in the 60s, and that's when Mercury and Gemini and Apollo were happening. I was 13 years old when Aldrin and Armstrong walked on the moon. And, I just, that was what always fascinated me. Mm-hmm.
What about popular culture, movies and so on, shows like Star Trek? Did they have any?
Actually less so. I've never been a big follower of science fiction. I was aware of that stuff, but it wasn't science fiction that drove me so much as it was real exploration as it was happening with things like Apollo, and then reading through the history of exploration and Cook and Columbus and Magellan and Scott and Amundsen in the Antarctic and that sort of stuff.
What about school before you went to college? Were you experiencing good science education, or was it really the home environment?
It was more the home environment. I went to high school and I took sort of the standard courses that you take, but to do the kind of science that I wanted to do when I was young, I wanted to design my own experiments and make my own mistakes, and it was really more at home. The really interesting science that I did and the things that I learned largely from my parents, actually.
Where did you do your undergraduate work?
I was at Cornell University. I was at Cornell as an undergraduate, as a graduate student, and now as a professor. I tried to escape from the place a couple times and didn't succeed either time. But when I was an undergraduate, I was a geology major. I'm a professor of astronomy now, but at the time I was doing just straight bang it with a hammer geology.
And what did you do your scientific work as a graduate student on? Did you do a dissertation?
Yeah. I was very fortunate in that I went to grad school. I was in grad school from 1978 to 1981, and that was right when the Voyager mission to Jupiter and Saturn was happening. And I was very lucky that I was able to work with the Voyager science team, and I wrote my thesis on 2 of the moons of Jupiter. It was just fantastic, very formative experience for me working on that mission. It was an incredible experience.
And was it the excitement of discovery, or was it that all of your education and your background was meeting in the right place?
It was
to
both.
be?
It was everything was perfect. I mean, all my background, all my interests were beautifully focused on, trying to do the geology of these moons of Jupiter. And then I got to, just be there and be part of it. We went from the moons of Jupiter being these little points of light, literally, that you could study in a telescope, into worlds that you could map and do geology on in 48 hours. It was phenomenal.
Before we talk about the Mars mission, I want to get your insights on being a scientist. What is the skill set beyond the obvious that really makes the kind of work you do possible?
Yeah, there are the obvious things, but I think the most important characteristic that you need to have to be a success as a scientist is just a deep and fundamental curiosity about how the world works. I mean, science is figuring stuff out. I always say that being a geologist is like being a detective at the scene of a crime. There are clues, and the clues are in the rocks, and you're trying to read those clues and figure out what happened at this place 3 billion years ago on Mars. And if you don't have that curiosity, I don't care how smart you are, I don't care how good you are at math, I don't care how well educated you are and where you went to school, if you don't wake up in the morning wanting to go figure out stuff, you're not going to really be a good scientist, because that's the key. It's having that curiosity drive you.
Mm-hmm. And the curiosity, and also involved in that, I guess, is posing the right questions, learning.
Yeah. That's actually that's a really important point. Is that if you look at scientists and you ask yourself who's successful and who's not, a big part of it really is picking the right questions to work on. And that has many dimensions. One dimension, just the practical one, is that if you want to do science, especially big, complicated science, you need funding, you need money. And so you got to pick a problem that somebody's willing to pay to have solved. And you got to write a proposal, and you got to get the funding to get that done. And that's just a practical reality. But the other thing is, if you want to have an impact as a scientist, you have to pick the problems that matter, the ones that are fundamental to our understanding. And those are sometimes not as obvious as you might think they would be. I mean, there are some that are obvious. Is there life on Mars? That's an easy one, okay? Mm-hmm. There are others that aren't obvious at first, and then somebody finds something cool, and off you go. So there's an element of intuition, I guess I would call it, having a sense of what's the important stuff to work on. Another thing is you need to be able to pick problems that actually are sort of solvable. I mean, there are important, exciting problems out there that are just intractable. And if you spend 20 years of your career banging your head against a brick wall and the wall doesn't fall down, you wasted 20 years. So you really want to be sure that you pick problems that you can actually make some headway on as well.
I think I read an interview with you, or maybe it was in the book, that part of your transition from geology to space was about, well, there would be more interesting questions out in space than there were on the ground here in geology. Is that a fair restatement of what you said, or is that not what you meant?
I wouldn't say it quite that way, but you're close. And this really gets to my passion for exploration as well as just pure science. I went into geology. It was the field that I chose, and spent several years getting trained to do geology. But after about 3 years of that as an undergraduate, what I came to realize is that the geologists who have been working on this planet for a couple hundred years have done a pretty darn good job of figuring things out. And while there was enormously important and interesting science that remained to be done, because I was driven by the desire to explore as well as to do science, I craved working in a field where there were things that had just never been seen, where there were problems that hadn't even emerged yet. And I was sort of drifting towards maybe doing some kind of work in the deep ocean, because the deep ocean is one of the most poorly understood portions of our planet. But then I got exposed to planetary exploration. I took a course at Cornell that was being taught by a professor there who was a member of the science team for the Viking mission to Mars. And this was going on at the time in the late 70s. And I was an undergraduate. It was a graduate level course. And we were expected, because it was a graduate course, to do some kind of piece of original research for our term paper. So a few weeks in the semester, I'm thinking to myself, I better start working on my term paper. So I go to this room where all the pictures from Mars were kept. And this is, of course, before CD-ROMs and internet and all that kind of stuff. And the pictures are just on rolls of photographic paper. And I remember walking into that room and sitting down and looking at these pictures of Mars that hardly anybody in the world had ever seen before. I was going to spend 15 or 20 minutes flipping through pictures. I walked out of that room 4 hours later knowing exactly what I wanted to do with the rest of my life, because this was the blank canvas that I had been looking for. I mean, I didn't understand what I was looking at in these pictures, but the beauty of it was nobody did. That was what appealed to me.
Now, in a project like the rover project, it's not just scientists; it's also engineers.
Oh, it sure is. You bet.
So,
yeah.
And you, in your book, you make an interesting distinction between the two.
Mm-hmm.
Tell us a little about engineers and
Yeah.
compare them with the work of science, which you just described.
Yeah, it's quite different. I mean, scientists are truth seekers. You're trying to understand how the world works, how the universe works. And that's what drives you. It's the curiosity about how things work. Engineers are creators, they're inventors, they're tinkerers, they're people who build stuff. And their goal is to build something that works and does so in an elegant, successful fashion. Engineers, because they're actually building real things, have to grapple with certain realities. You have a finite budget to build something. You maybe have a finite schedule. Certainly if you're sending spacecraft off to Mars, you have a launch date and you better make that launch date. And so engineers have to make compromises. They might have a concept in their head for what would be the most elegant machine you can imagine to accomplish this task, but it costs too much, it would take too long to build it, etc. And so you have to come up with something that works. And so there's this very interesting interaction that takes place between scientists and engineers, where the scientist has some concept for, I want a machine that will do this. So I go and talk to an engineer, and the engineer says, well, yeah, we could try that. Let's see what we can do. But then, of course, the scientist wants it to be perfect. The engineer wants it to work. And those two are sort of in conflict with one another in the real world when you have these schedule constraints and budget constraints. And so there's this very interesting interplay that goes back and forth between scientists. And it can be wonderful or it can go very wrong. And when it's wonderful, as it was on our rover mission, it's, there's this wonderful creative interplay that takes place. And what I found was that the key to making it work is that the scientists need to learn some engineering, and the engineers need to learn some science. And so we put a lot of effort on our project into achieving that. And I give a whole lot of credit to our project manager, the engineer who sort of led the engineering team, because he kind of instilled the view among the engineers that we're doing this for the science. And I tried very hard with my science team to hammer into them that, if the engineering doesn't work, we get nothing. And so we got to learn some engineering. We got to respect what the engineers do. And I'll bet you that if you came and you sat in on one of our daily tactical planning sessions, where we have a team of, a dozen scientists and a dozen engineers sitting together in a room and figuring out exactly what we're going to do with the rovers on Mars, I bet you could sit there for an hour and still not quite figure out who were the scientists and who were the engineers. The team has blended so well now that I think you'd have a hard time telling the difference.
Now, it's very clear in reading your book and watching the movie, which is also very good. I should mention that a Disney-produced movie with the same title, Roving Mars, that you had the important role of being the leader. So you're not just a scientist working with engineers, you're the leader of a science mission project. So let's talk a little about that role. So what are the characteristics that make it work, and how do you learn as the process goes on?
Well, you learn by making mistakes and doing the best you can. You know, I'm the leader of the science team for the mission, and you know, you can't boss scientists around. You're not the general in an army with a bunch of privates under you that you tell what to do. Okay, scientists do what they do because they love what they do, and they're creative, and they work best when they're allowed to exercise that creativity. So the way we tried to lead on this project, and it was, in some respects, I think it was similar with the engineers too. I mean, we had a very, very talented engineering team. These are people who had a tough job to do. They needed to create something. And what you do when you're leading a group of people like that is, rather than giving them a lot of directives, writing a lot of memos and giving a lot of orders, what you want to do instead is make sure everybody knows what their job is. You create a structure in which everybody has a clearly defined responsibility. You make sure that they know the processes that they're supposed to follow to get that job done. And then you kind of stand back and let the machinery work. And you know, I think the best leader of an organization like this is one who gives no orders at all. That you create an organization that runs so well that you can take your hands off and just let it go. And you know, I'm proud that I think we've achieved that. I mean, I could get hit by a bus today and the Rovers would never know. You know, my team is so good, they don't need me. They don't need me. And you know, another thing is, if you create an organization in which any person, the leader or anybody else, is indispensable, irreplaceable, you've made a mistake. You know, if you're spending 900 million taxpayer dollars, which we are, you better not have anybody who is just essential, because stuff can happen. And so, you know, we've worked really hard to create an organization where everybody knows their job, things go well. You know, I'm here at Berkeley today. The rovers are going to be operated. The science team is going to be meeting. In fact, they're meeting right now as we're speaking, now that I think about it, planning the next day's worth of operations on Mars. And I don't know what they're doing, but I know they're doing it well, because they always do.
It's an interesting expression, the rovers. When you use that expression, you're not just talking about the robots. You're talking about the team that are actually part, or was that just a...
Yeah, you know, it all sort of blends together in your mind after a while. We see these rovers as extensions of ourselves. You know, we want to understand Mars. We want to explore Mars. If any of us had the ability to strap on our boots and our space helmets and go there ourselves, we would. Instead, we experience Mars through the rover's eyes. We touch Mars with the rover's arm. And you know, that eyesight, that arm, they're very human-like, and that's you know, some of it's coincidence, but some of it's quite intentional. And you see yourself as almost being there virtually through the rovers, and it's, you know, you're standing there on Mars, kind of, and you look around with the cameras, and you think, oh, that looks interesting. Let's go there. And then you do. And the next day you're there, and there are pictures of what you wanted to see close up, and it's so much like being there. And yeah, it kind of blends together in your head a little bit after a while.
Now all this comes about, and we'll talk a little more about the rovers and the mission in a minute. It is very interesting, because in your book you describe that this particular project was kind of the third or fourth proposal. So you had to deal with the frustration of writing proposals, that weren't funded, didn't win the competition. Talk a little about that, because there is an interface here, big science, big engineering teams, but you have to go to the government to be funded and win in a competition.
Yeah, you do. And that's the way it should be. There are a lot of ideas out there for interesting things that you can do in space, and they all cost a lot of money. I mean, an inexpensive planetary mission costs $500 million. Okay, these are phenomenally expensive things. And there are lots of great ideas out there, far more good ideas than you can actually fund and carry out. And so how do you decide what to fly? It's largely via a competitive process. And yeah, we went through a period. I mean, I started writing proposals for what eventually became this mission in 1987. We finally got selected for proposals, and 10 years later, in 1997. And there was a string of failed proposals in there. Each one was better than the one before. And frankly, the early ones probably weren't good enough, and they didn't deserve to be selected. They weren't at the level of quality that it made sense for the American taxpayers to invest hundreds of millions of dollars in our idea, because our idea wasn't good enough yet. And it was bitterly disappointing when you put years of effort and hundreds of thousands of dollars into writing a proposal and gets shot down. But looking back on it, they probably deserved to be shot down. I can see the flaws. And we got smarter, and we got better, and we honed our ideas, and there was stuff that we would have liked to have done that we had to take out because we had to make compromises to make it all fit. Then in the end, finally, 1997, after 10 years of writing proposals, we got selected to do a mission. And then there was great turmoil in the Mars program. We got flat out canceled and brought back to life 3 times. And it wasn't really until the year 2000 that we got the final go-ahead from NASA to build these 2 rovers. We initially thought we were going to build 1, and then they decided to fly 2. And once they sort of made the decision and gave us the money, we had 34 months to actually do it before we had to be on top of the rockets in Florida. It was, there was this brutally long period of writing proposals and trying to get NASA to say yes. And then once they finally said yes, there was this brutally short period of time that we had to actually get it done.
Mm-hmm. Now, tell us what there's one point I did want to bring out, because in your book there's this beautiful description of each time you would be writing a proposal, you would get a group together, and you struggle with a blank piece of paper, and you sort of had to put it all down.
Yeah.
So all of this losing, then winning, actually competing, but then bringing on board former competitors and so on, is all part of that.
Oh yeah, it's this very complicated evolutionary process. And like you said, it starts with the blank sheet of paper. The blank sheet of paper phase is actually one of my favorite parts of the whole space mission game, but it's a scary part because, boy, you can go terribly wrong in that phase and have very bad consequences downstream. The blank sheet of paper is literally, you got an idea. I want to find out what it was like on Mars 4 billion years ago, and could the conditions there have supported life. I know that the basic approach to doing that sort of thing that works on Earth is you go and you do field geology and you look at the rocks and you read the story in the rocks. So that's what I want to do. Okay, now how do I do it? I mean, how do I actually build a piece of hardware that you can strap on top of a rocket and shoot off to Mars and it's actually going to work? And you sit down and you gather colleagues, friends, people who you know who are really smart and good at this kind of stuff, and you start throwing around ideas. Well, we could try this. Well, we could try that. And oh man, we went through so many. There were iterations of this mission where the rover would descend on this powered lander, it would land, look around, and then take off again and go land somewhere else. We had all sorts of ideas. Many of them turned out to be impractical, including that one. But you fill in that blank sheet of paper with your ideas. And then you put in a proposal and you compete. And you compete against other colleagues who have similar ideas. And maybe you succeed and maybe you fail. Most of the time you fail. And when that happens, it feels really bad. Then you kind of regroup and you say, okay, what are we going to try now? And sometimes, as you said, you approach some of your competitors and you say, well, we've got a good idea, but you've got a pretty good idea there too. You want to team up maybe? And so there's a lot of that stuff that goes on. And yeah, we went through 10 years of that stuff before NASA finally said yes.
Help us understand better now why Mars. You touched on that in a minute. I mean, what when you go for Mars, what is it that our audience should understand about Mars, and what makes it attractive for a scientist to go after the question you're looking at?
The thing that makes Mars important is that it's one of the few places in our solar system that's enough like Earth that you can imagine life having once taken hold there. And in fact, while it's sort of like Earth today, there's strong evidence, powerful evidence, that in the past it was more like Earth. It was warmer, it was wetter, there was liquid water at the surface. You can see places on Mars where it looks like water pooled and ponded and flowed and so forth. And so, because water is such a crucial ingredient for life, Mars becomes a compelling target to try to answer the question of, are we the only life in the solar system, or has life taken hold somewhere else? Now, Mars is not the only place you can do that. Another world that I'm very fascinated by and have been for years is Europa. And Europa is a big moon of Jupiter. It has a crust of ice, and we think below that crust may be an ocean of liquid water. And if I could figure out how to do submarines on Europa, maybe I wouldn't be doing rovers on Mars. But Mars is both important to the question of life and comparatively accessible. You can actually build a robot and go to rock outcrops on Mars that preserve evidence of what it was like long ago, and read that record and infer things about what the planet was like. And so that was what drove us. It's the life question. I mean, that's what makes Mars special.
And how far away is Mars? If we're planning a vacation, how long is it going to take to get there? And
yeah,
so
you better be ready for a long trip. Mars is roughly 50% farther from the sun than the Earth is. Of course, the planets are always moving, so the distance between Earth and Mars is always changing. When you launch from Earth to go to Mars, typical travel time is maybe 7 months, 6 to 8 months. It took us 7 months to get there, and that's a long trip.
And did you know how much money you would have in the beginning, or did the amount of money you have change over time?
Oh my, it changed. When NASA first asked us to do this and told us they wanted 2 rovers, we did the very best we could to estimate what it was going to cost. And I remember the number. It was $688 million. And we were sure. I mean, we had all sorts of margin on top of that. We were quite confident in that number. As it turns out, we were wrong. And our budget overran. And in the end, it cost about $800 million to get the rovers to Mars. And then we've spent another $100 million since then operating them. So we underestimated. That's not uncommon in the space business. You're trying to do something that nobody's ever done before, so it's hard to guess exactly what it's going to cost, because it's difficult to foresee the problems you're going to encounter. We encountered many terrible problems in the process of building our rovers, but the bad ones all stemmed from one thing. We underestimated how big the rover had to be by about 10%, just by a little bit. Okay, we had a design for a lander, for a parachute, for airbags, all that stuff that we had inherited from a previous mission. There was the Mars Pathfinder mission, wonderful mission, back in the mid-90s. And the idea, we were just going to scoop out the interior of the Pathfinder lander so we have a big empty space and stuff our rover in there. And if the rover fit, we really could have done it for $688 million. But in the end, the rover was just a little too big to fit. So the lander had to get bigger. So everything got heavier. So the airbags needed to be reinforced, and the parachute had to be redesigned, and everything changed. We had to redesign the whole landing system. And that resulted in a cost overrun, and in the end it cost about $800 million.
Now, this team that was working on these sets of problems that were changing over time, you attempt in the back of your book to list them. There are 4,000 plus, really.
Yeah. And the real number is probably something like 6,000 or 7,000. I couldn't find them all, but yeah, there were thousands of people who worked on this mission.
And so organizationally, you confront a problem. You mentioned one, the parachute problem. The rover is getting bigger and bigger, and you have 8 months to launch, and the parachute you have sort of doesn't work.
Yeah.
Organizationally, what happens as you confront that problem? Is it clear the subgroup that this problem goes to, and they're off working on it? And so on?
Yeah. I mean, you have to have clearly delineated responsibilities. When a problem comes up, you got to be very certain who owns that problem and whose responsibility is to find a solution to it. So in the case of the parachutes, we had a small group of individuals led by one very talented, creative person whose job it was to solve that problem. The approach they took was, man, we're almost out of time. Let's develop 3 different parachutes in parallel and hope that one of them works. And one of them did. But that was a scary problem, and one among many. I mean, we had all sorts of terrible things go wrong over the course of developing these rovers. And to me, it was a small miracle that we even got to the launch pad, let alone Mars.
When you think of a scientist working in a lab and creativity, the light bulb goes off.
Right.
If we were a Disney cartoon, what is creativity like in a group process like this? In other words, is it that you confront a problem, the right team with the right relationships working together, and then a bulb goes off?
It can work in different ways. It depends on the particular problem and the nature of it. It is very much a team effort. These rovers are so complicated that no one understands them. There literally is no single human being who understands these rovers. They're just too complicated for a single person to wrap their head around completely. As a team, we understand them. As a team, there's somebody who understands each part of the vehicle well enough that as an organization, we get it. But when you're in the process of creating something that complex, it's a mix. It's a mix because there are some problems that you really require group interaction to deal with. You've got some problem that you're working on, and it has many, many different elements to it. And there's no single person who is going to be able to solve that problem on their own. In other instances, there were a number of things that were solved by, the lone genius, if you will. We had a lot of geniuses on our team, I think. And, one person somewhere has some brilliant insight, and then you go, oh yeah, that's got to be it, and you go charging off down that path. But it was one person's instant of creativity when they saw the solution that nobody else saw. And I give some examples of that in the book, that we had what looked like some insurmountable problem, and somebody goes, oh wait, why don't we try this? And everybody goes, by golly, yeah, that's it, So it's a mix. But, looking at it, I think a lot of the most important, really creative moments in the design of this thing came from the insights of specific individuals, people whose job it was to solve this problem, and they just sat down and solved it.
There's one episode, once the rovers are there, that sort of struck me, and briefly, you lose contact with the rover.
Spirit,
you can't,
yeah.
you can't figure it out.
Yeah, it
and
was
there was a problem with the flash drive, and it's very interesting because it was as if the rover had died.
Yep.
You're all running around, but somebody
I didn't sleep for 3 days.
But somebody, one member of the team,
Glenn Reeves,
brilliant
guy,
had done what and
Yep.
he. So it's an example of a kind of creativity that anticipated something.
Yes.
In the
that was a
future.
wonderful example. What happened was 18 days into the mission, we just lost contact with Spirit, just gone. Nothing. And the way you troubleshoot a problem on a spacecraft is you look at the data that you have in the telemetry, you figure out what's going on, and you fix it. The only thing we had was no telemetry. That was really bad. And then what happened was we started to get just little blips of data from the rover, and we finally sort of got the sense that what was happening was the computer was booting up, it recognized the problem, it crashed, and then it would boot up again 15 minutes later. It was doing this over and over and over, and doing it during the night when there's no solar power, and the battery's going down and down and down and down, and sooner or later, 4 or 5 days of that, and the vehicle's going to die. So we had a real problem on our hands. And we didn't know what was going on because we get these little tiny fragments of data. But what Glenn noticed, this was the breakthrough, was that Glenn started looking at just these little tiny blips of data that we would get. And what he noticed was that it was all what we call real-time data. In other words, it's the rover saying, here's what's happening to me now. Here's what's happening to me now. Here's what's happening to me now. None of it was, this is what happened an hour ago, or a day ago, or 3 minutes ago. It was all real-time stuff. And what that meant, Glenn figured out, was that the rover had no memory. It could only say what was going on at the time. And during the development of the rovers, we had a lot of problems with the flash memory on board the vehicle. And because of that, Glenn had created this command. It was called init crippled, initialize in crippled mode. And what it does is, rather than using the flash memory, it builds a whole little file system in RAM in the computer instead. And so we fired up, based on his intuition, an init crippled command, and boom, the rover regained its sanity immediately. And it was a problem with the flash management software. And once we regained control of the vehicle and put it to sleep to recharge the batteries for a couple days, then it was possible to figure out what was going on, regain control, and everything was fine after that. But there was that moment of insight when Glenn realized, oh, it's all real-time data. It's probably the flash. That was the thing that saved the mission. If it had gone for another couple days, we would have lost Spirit.
Mm-hmm. Now, help our audience understand the rovers, basically.
Good luck with that.
I realize we could take hours doing that, but just sort of briefly, first, how were they named?
Oh, yeah. Spirit and Opportunity. The way they were named was that NASA held, I don't know if I'd call it a competition, but an activity in which school children across the country were invited to write in and suggest names and write a short essay. And then there was this process to select the names from that pool. And the names Spirit and Opportunity were suggested by a little girl. I think she was about 9 years old at the time. She was from Arizona, near Phoenix. Her name was Sophie Collis. And she had been born in Russia and grew up initially in an orphanage there. She lived in an orphanage in Russia until she was about, I think, 4 years old, something like that. And she at the age of 9 could remember some of her time in the orphanage. And then she had been adopted by an American family and had come to the United States. And she wrote this very touching essay. It was like 3 sentences long or something. I mean, she's 9 years old. But she had picked the name Spirit and Opportunity to sort of represent her feelings about the opportunity that she got to come and start her life over in the United States. And I've actually grown very attached to those two names. I thought they were wonderful choices. One of the things I liked about it is those names sort of follow in the tradition of naming ships of exploration after things that express your hopes, your aspirations. Endeavour, okay, one of the space shuttles, but also named after James Cook's ship on his first voyage of circumnavigation. Great example of that. And Endurance, Ernest Shackleton's ship. I mean, there are many, many good examples like that from history. So I think Spirit and Opportunity are great names. And
interestingly enough, the names sort of worked as you described what the two did. Opportunity had opportunity, and Spirit had Spirit.
Spirit needed a lot of Spirit, yeah. It's funny because the rovers, yeah, I mean, they're hunks of metal, okay, I get that. They're robots, but they're complicated enough. They sort of have developed a certain amount of personality, right? We made them as identical as we could, but of course they're so complicated that they have differences between them anyway.
What can they do? Talk as you're answering the question. Yeah.
And then once we got them to Mars, we wound up operating them in very, very different environments and in very, very different ways, and so they've had very different experiences since they got to Mars. In Opportunity's case, the big scientific discoveries all came in the first 6 weeks. I mean, it was just right there, right there. It was easy. Spirit had to work for everything. I mean, Spirit landed in this horrible, rocky lava plain with boulders strewn everywhere and had to struggle to get to these hills and then, climb a mountain to start finding the really interesting science. I mean, what the rovers do is just what you would do if you were there. There's sort of 3 key components. One is they can look around. They've got very good cameras with the equivalent of 20/20 vision. They've got, Superman's got X-ray vision. We've got infrared vision. We can look off in the infrared and use that to figure out what rocks are made of from, 50, 100 meters away. When you find something interesting, the second thing that they can do is move. They can go over and, just like you would, oh, that looks like an interesting outcrop. Let's go look at that. So you walk over to it. Okay, we drive over to it. Then when you get close, you can investigate it in detail. And we've got this arm, and it's got the same dimensions as a human arm. And on the end of it, there's this suite of sensors that includes a microscope, this thing we call the rat that can grind away the outer layers of a rock. We've got spectrometers that can look at the rock and tell us what it's made of. And those really gather the in-depth clues that we can use to figure out what happened here. And it's just this constant process of discovery. You land with an idea. At both landing sites, we landed with an idea of what we were going to find. Totally, completely, utterly wrong. Could not have been more wrong at both landing sites. Okay, so then you kind of regroup, and you say, okay, this is different. Now what are we dealing with? And you just explore. And it's so much like what real geologists do on Earth when they're in the field and doing what geologists do. It's real field geology on another planet, and it's fun.
Yeah, as you describe the humans on Earth interacting with the robots, I had this sense that it was a combination of an ER, a family intervention, and parents communicating with their children away at college who were dealing with a problem. Is that fair?
Yeah, there are elements of that. I would also throw in, maybe operating a robotic, remote-controlled car or something. There are elements of many aspects of that. The rovers, we designed them to be as capable and as flexible as we could. Sort of like a Swiss Army knife. You equip them with lots and lots of tools. You don't actually know what tools you're going to need. I mean, the environment that we were sending them into was so poorly known that we couldn't design for that environment because we didn't know what it was. We didn't know what things we were going to encounter. So you have to just kind of imagine the things you might find and imagine the tools that might help you figure those things out, and then build those tools and cross your fingers and hope for the best. And you get there, and what you find is not what you expected. The tools you brought are pretty good, but maybe not exactly what you would have built for the circumstances you encounter. So then you start getting creative, and you start figuring out how to use the tools you got to answer the problem that Mars has given you as opposed to the one that you anticipated. And you improvise. You make stuff up as you go along. We didn't know what we were doing when we landed. I mean, how can you know what you're doing when nobody's ever done it before, right? Mm-hmm. So you just figure it out as best you can. And another element, of course, is that you command the rover to do certain things. But all of those things depend on how it interacts with Mars. You turn the wheels to get it to go, but sometimes the wheels slip in the soil. Okay, you want to take a picture of something, but you get close to it and it doesn't look like what you thought it was going to look like. And so sometimes you tell the rover to do something and the result that you get is not quite what you expected. I mean, we've gotten them stuck in sand dunes. All sorts of things have happened. And when that happens, you just figure it out. And also stuff goes wrong. I mean, things break. These rovers are getting old. They're 7 years old, and hardware breaks on these things. And when the hardware breaks, you can't go up with a screwdriver and fix it. You got to figure out how to work around it. And so there's this process of just figuring out how to deal with the unexpected. That's part of what makes the operations fun. I mean, the constant discoveries, the scientific discoveries, are tremendous fun. But this challenge of taking this thing that we built and trying to make it work in this crazy, unexpected, unpredictable environment that's a fascinating challenge as well.
In your lecture, you said that the rovers were programmed to have courage, to make choices. Talk a little about that, because it's not all your guidance.
That's right.
Yeah.
That's right. I mean, when you think about this, the rovers they're very far away. A typical time that it takes to send the radio signal to Mars might be 10 minutes, okay? So you can't joystick it. You can't operate it in real time. You have to send a set of commands. And typically what we do is we'll send an entire Mars day's worth of commands all at once. It gets those commands first thing in the morning, and then we don't communicate with it. We told it what to do for the day, and it does it, and at the end of the day, it sends back the results. And sometimes you have to ask the rover to make its own decisions. I mean, let's say we want to drive long distances. We want to drive, with Opportunity right now, we're trying to drive like 150 meters a day. That's a long ways. We have good cameras, but the cameras are not good enough to reliably spot dangerous obstacles 150 meters off in the distance. We just can't do that. So you got two choices. Either you can say we're only going to drive as far as we're confident we can see, which slows you down, or you can trust the rover to look at the terrain in front of it on its own and make smart choices. And we've built that capability into the vehicle. So typically when we do a long drive, the first part of it, maybe the first 70 or 80 meters, we will command explicit. We'll just tell the rover, go. Okay, we can see, we know it's safe, just go. Go as fast as you can. But then once you get 80 meters out, we want you to turn on your brain, and we want you to start looking ahead. And what the rover will do is use its cameras to look for obstacles, and it can do onboard stereo matching. So it takes two images, uses those images to build up a three-dimensional model of the terrain in front of it, and it'll assess what it sees. And if it looks smooth and flat and smooth sailing, it'll move forward. If it sees an obstacle, it'll look at that obstacle and say, well, is that little enough that I can drive over it, or should maybe I go around this thing? And yeah, you can program different levels of courage or cowardice. You can make it scared of only big objects, or you can, if you think it's really dangerous out there, you can make it scared of little tiny ones. In that way, the rover is able to kind of pick its way through what might otherwise be risky, dangerous obstacles.
What is the most important thing that you think we've learned from this mission?
Well, that's a hard question. It's been going on for 7 years now, and we've made many individual discoveries. But if you take the most important individual discoveries and kind of wrap them together and say, what did we really learn? What we've learned is that in the past, Mars clearly had habitable conditions on its surface. There was liquid water below the surface. There was liquid water that came up to the surface. There were hot springs. There were volcanic vents with steam coming out of them. There were places that on Earth are inhabited by microbial life. Now, that doesn't mean that happened on Mars. Being habitable and being inhabited are two different things. But there clearly were times and places on Mars where conditions would have been suitable for life. And so what that says is, if you want to know whether there truly was life on Mars, you go to those places with the right tools and you investigate the question of, was there life? Maybe the best way is to bring rocks back and put them into laboratories on Earth. But was Mars once a habitable world? Yeah, there were places and times where it was.
Now, I know that you have been chairman of an advisory committee to sort of look at the future of space.
That's been my other job for the last couple of years.
I mean, the country is in a place where it has to reassess its priorities and so on. So how should we think about what we should do in the future? This mission was such a great success in the sense that the rovers have gone more than how many days? I mean,
today, as we speak, is day 2,586.
So building on that, you know, sort of great achievement of scientific leadership, how should we think about the future?
Well, we can talk just about Mars, or we can talk more broadly. As you say, one of the things I've been involved in recently is it's called the Planetary Decadal Survey, and it's a years-long process of establishing priorities for the next decade of solar system exploration. And the conclusion from that process was that the next thing to do at Mars, after we've completed the missions that are in the works right now, is to bring samples back, is to bring rocks back from the Martian surface. We've gotten to the point where we know enough about Mars that we know the good places to go. And it's so hard to build instruments that you can miniaturize and ruggedize and put on top of a rocket and send to Mars. The best scientific instruments are always going to be back here on Earth. And so the next logical step for Mars, now that we've learned all the things we've learned, is to find some of these really critical rocks that are most likely to contain clues about life and bring them back to this planet. And so that is the next step for Mars. But there are other great places to go as well. I mentioned Europa. Europa is this moon of Jupiter that we think has an ocean, and it'd be nice to really understand that ocean. And so there's a mission that we're looking at and thinking about that would go into orbit around Europa and would carry a number of instruments. You know, an intriguing one is a long wavelength radar. I mean, radar at long wavelengths can actually see through kilometers of ice. That's how we've mapped the bottom of the Antarctic and the Greenland ice sheets. Do that at Europa. Find out how thick that ice is. Find out how deep you have to go to get to the ocean. Find where the thin spots are, so maybe someday in the distant future we can go there and get down into the ocean. So that's a very exciting mission. Another mission that we're really excited about is a mission to Uranus or Neptune. There are basically three different kinds of planets in the solar system. You've got the terrestrial planets, Mercury, Venus, Earth, Mars, and made of rock. We've explored those very well. You got the gas giants, Jupiter and Saturn, made mostly of hydrogen and helium. We've explored Jupiter with Galileo. We've explored Saturn with the Cassini mission, which is going on right now. And then you've got the ice giants, Uranus and Neptune, which they're made of very, very different stuff than Jupiter and Saturn are. They're not like anything else, and all we've done is fly by them, each of them once, with Voyager 2 with 1970s technology. And so there's enormous potential for discovery there. And so another future mission would be a kind of an orbiter and a probe to go to one of those ice giant planets. So those are some of the really exciting things, I think, on the horizon.
How critical is this work in the future, in our future in space, to maintaining American scientific leadership?
Oh, I think it's crucial. I think it's absolutely crucial. I mean, if you look at the things that our nation does scientifically, there are only a few, really. If you look at the capabilities that exist in many countries now, there are only a few things where we in the United States are still the acknowledged world leaders, and we do stuff that nobody else can do. You know, high energy particle accelerators. The Europeans are great at that, okay? I mean, you can name all sorts of things where the United States is not the acknowledged leader, but this is an area where we are. Okay, planetary exploration, deep space exploration, this is something that we do better than anybody. And if you want to talk about maintaining leadership, man, here's a great example.
Finally, how would you advise students out there who might watch this to prepare for the future if they see their future is involved in this kind of work?
You know, it comes down to the fundamentals. It's when you're getting your initial training, it's blocking and tackling. It's the really basic skills. There's plenty of time once you get into graduate school to specialize and learn about this detail or that detail or what have you. The foundation on which all of this is built is physics, chemistry, mathematics. Okay, the real core sciences that we need that form the toolkit that you use to do this kind of stuff. And we talked earlier about creativity, and we talked earlier about insight and people's ability to look at some tough problem like a parachute that doesn't work, or how do you position instruments with a precision of millimeters on another world. Those problems were solved by creative people, but every single one of those people had a solid background in physics, mathematics, the things that you need, the toolkit that you need to solve problems like that. I don't care how creative you are, if you don't have those tools, you're not going to be able to do it. So in the beginning, it's just getting that solid grounding in the fundamentals.
Steve, let me show your book again. I think people will really find it fascinating. And also there is an IMAX movie which really gives you a visual sense of a lot of what you were describing. Thank you very much for coming on our program.
I enjoyed talking to you.
And thank you very much for joining us for this conversation with history.